Hello, my name is Yipei Wang and I'm from Purdue University. Today I'm gonna give you an introduction about benchmarking deletion metrics with the principled explanations, a recent work accepted in ICML 2024. Data-driven machine learning models, especially deep models, are usually considered as black boxes. A black box model takes a high-dimensional input and maps it to the prediction y-hat without providing any explanation to such a process. In order to review the internal mechanism, attribution-based explanation methods provide explanations by assigning an attribution score to each input feature, indicating their contributions, sensitivities, or importances. Here are some examples of attribution methods explaining DNNs and ImageNet. However, one important problem of attribution methods is that there are just countless attribution methods, such as gradcam, excitation backpropagation, rise, extremal perturbation, information bottleneck attribution, gradient-based methods, and etc. etc. And different explanations usually provide distinct explanations even for the same model and input pairs. Therefore, it is very important to be able to evaluate these attribution-based explanations. The most popular and widely used explanation metric is the insertion-deletion metric. It appears in almost all literatures that involves evaluating attribution methods. Here, we use gradcam as an example to show how it works. Given an input image and a prediction, attribution methods such as gradcam provides a heat map representing the important values of features. Then, deletion metrics gradually delete features regarding the attribution values. After each feature is deleted, the prediction of the target class is recorded as the measure. By differentiating the order between most relevant first and least relevant first, different results are expected. When features with higher attribution values are deleted first, that is, MORF, the prediction is expected to drop faster, resulting in a smaller AUC. And then, when features with lower attribution values are deleted first, that is, LERF, the AUC is expected to be larger. However, although deletion insertion metrics are the most popular and widely used metrics, there are many challenges that hinder a faithful application of such metrics. There are a lot of unjustified criteria, such as whether to use the predicted probability or the logic of the target class as the indicator, or whether to use the insertion or deletion as the progression, or like the choices between LERF versus MORF. Note that also since DNNs usually take input of a fixed size, deleted features have to be imputed with reference values, and choices of such reference values can have potential implications to the evaluation results. Besides, there are also other considerations such as whether to delete features as the smallest unit such as pixels or as the grouped features such as superpixel patches. Here we demonstrate the consequences of different criteria through the out-of-distribution issue. With different criteria, LERF versus MORF, and 3 different reference values, the evaluation results of 3 methods, gradcam, integrated gradient, and gradient, can be very different. And this contradicts the purpose of a metric, which is to select the proper attribution methods out of different explanation choices. To carry out a rigorous study regarding the metrics, we first look into the desiderata of different criteria. That is, what does it mean by applying deletion metrics, and what are we expecting from the explanations being evaluated? Note that given an explanation psi, using deletion metrics implies that a desired attribution method should have larger AUC under LERF and lower AUC under MORF. Therefore, it is equivalent to recognizing the explanation that has the highest LERF AUC or lowest MORF AUC as the best explanation of deletion process, or the principled explanation of deletion metrics. However, Such attribution methods that achieves the highest possible scores remains unknown. To obtain the principled explanation of the deletion metric, we need to solve the following optimization problem. Given a model input pair f and x, we need to find the attribution map psi that minimizes the MORF AUC and or maximizes the LERF AUC. This is infeasible since the computation of AUC is non-differentiable and it requires searching the entire Euclidean space R to the power of d. In this work, we propose trajectory importance, aka trace, to solve this previously infeasible problem. First, we build a canonical projection from the d-dimensional Euclidean space to the symmetric group S sub d. It maps the attribution psi to a unique permutation tau. Then there exists an equivalence relation R between attribution maps. Two attribution maps are said to be equivalent if they are mapped to the same permutation, that is, the same deletion trajectory of features. Therefore, we can then quotient out the specific attribution values and rewrite the optimization problem regarding the permutation tau over the symmetric group. Under the new formulation, such optimization can be solved by various of combinatorial optimization algorithms, such as simulated annealing, generic algorithm, type search, and etc. In this paper, we employ simulated annealing, but also tested other choices in appendix. Basically, starting from an initial state tau 0, we iteratively search other deletion trajectories from its neighbors to find the optimal deletion trajectory. Please refer to the manuscript for the definitions of neighbors and other details such as the algorithm. As a baseline, we also include a heuristic method that deletes the features one by one in a greedy manner. Recall that in the MORF and LERF results of GradCam on one input, which according to recent studies is still in the tier 1 of explanation methods under deletion metrics. Previously, without the principled explanation from trace, one may think that this is already a very good result and close to the bounds. However, compared with the results of trace, we can see that the discrepancy is still significant. The predicted probability of the target class can even increase after deleting several features. And on the right-hand side are the comparison between trace and some popular attribution methods under LERF and MORF. We also test the results regarding predicted logit and the probability. Trace P and trace Y are optimized regarding probability and logit respectively, and it can be observed that although they both outperform existing explanation methods by a significant margin, they also outperform each other regarding their own test. This suggests a potential differences between using probability and logits as the indicator. Combine the LERF and MORF together, represent the quantitative results of the difference between LERF AUC and the MORF AUC, which is expected to be the higher the better. It can be clearly observed how trace pushes to the limit of deletion metrics compared with existing attribution-based methods. The comparison with existing attribution methods is only a necessity condition for trace to be the principled explanation. Note that combinatorial optimization algorithms do not grant a global optimum. Therefore, we inspect how close trace is approaching the global optimum. This is achieved by the upper and lower bounds of complete search. Take MORF for example. When the K features are deleted, complete search finds the optimal subset of features of cardinality K that minimizes the prediction. And then the summation over all sizes K from 1 to D forms a lower bound of MORF AUC. Note that this lower bound is in general infeasible because the deleted features in each step can differ from each other and do not form a trajectory. The comparison is shown on the right. It can be observed that trace approximates such upper and lower bounds very well, and the true global optimum can only lie between trace and complete search, which is a very small area. Another important issue of deletion metrics is the out-of-distribution problem. It refers to the phenomenon that deleting a small portion of features changes the prediction greatly by breaking the original distribution of the input instead of by removing important features. Therefore, it's hard to tell if the prediction drop is due to the break of distribution or due to the removal of really informative features. It is also affected by the reference values. Zero imputations completely remove the feature, but also breaks the distribution significantly. Blur imputations, on the other hand, preserves the distribution, but at the cost of not deleting the features completely. To rule out the influence of informative features, we delete features in a completely random manner with different patch sizes, and the deleted features are imputed with zeros and Gaussian blurs. Since zeros and blurs represent the discrepancy brought by the OOD issue, the larger their differences are, the more severe the OOD issue is. It can be observed that with different references, the trends differ even when the feature sizes are identical. However, as the size increases, the influence of OOD decreases. And when the features are deleted as 32 by 32 superpixels, the OOD issue is almost eliminated. Finally, based on the experimental results of trace, we can have the following conclusions regarding the deletion metrics. First, probability and logit should be handled according to the targets of the interest as they give completely different results. Second, image features should be deleted as superpixel patches instead of raw pixels. Third, reference values do not have significant influence when deleting with patches. Finally, in terms of evaluation direction, we suggest that the LERF minus MORF is the best one and is better than LERF, and both of them are much better than using MORF as it's corresponding with the OOD issue. In addition to benchmarking the deletion metrics, we can notice that trace also provides the principled explanation regarding deletion metrics. The popularity of deletion metrics reveals that the optimal deletion trajectories are always desired in understanding feature importances. And trace, to our best knowledge, is the first to solve for the optimal trajectories, and it brings up a lot of ideal properties such as faithfulness, model agnosticism, robustness to attack, and also clear interpretations and etc. For details of these properties, please refer to the manuscript. And thank you. That's all for the presentation.